I'll make a note to myself to look at it. All right. So, what are we going to be talking about today? We're going to be talking about Thevenin and Norton equivalent sources, which are shown behind me here. This is chapter 5 in the book, so we're still moving pretty linearly through, progressing through the book. So what are Thevenin and Norton equivalent sources? These are two basic types of sources which one has an internal voltage, the other has an internal current, and then we have a source resistance for both of them. For the Thevenin source, the resistance is in series with the voltage, and for the Norton, the resistance is in parallel with the current. Now, these two sources are equivalent to one another, meaning that we can convert back and forth between them, which is an interesting characteristic of Thevenin and Norton equivalent sources. But what we're going to spend more time talking about today is our ability to take more complex circuits and boil them down into one of these two. So let's say we have a circuit that's made of independent and dependent voltage and current sources, a whole bunch of different resistors. But we're only concerned with what's happening at terminals A and B of that really complicated circuit. Then what we can do is there's a method we can use. We can boil it down to this version here, and then let's say we want to test how this circuit reacts to different loads or different, whatever we might be connecting to it. So as opposed to having to analyze that more complicated circuit each time we do our test, now we can use the simpler version, which I'm sure you can see has a lot of advantage, especially if you were doing it by hand. Not that you would necessarily be doing it by hand, but it would make it easier to find your answer each time. So the Thornton and Norton, Thevenin and Norton sources are not only equivalent to each other, but they are also equivalent to more complex circuits, assuming that we do everything properly. Okay, now one important thing to note about the Thevenin and Norton equivalent sources is that we can only see what's going on at the load or the output terminals. So we can only observe this, VL and IL. So when we talk about the Thevenin and Norton equivalent sources, we are going to be using VL and IL to try to figure out what's going on inside of the circuit. So how do we convert between the two of them? It's actually very easy. You just use Ohm's Law. So let's say you're trying to go Thevenin to Norton, right? Then what you would have is I Norton is equal to V Thevenin divided by RS. Let's say you're trying to go Norton to Thevenin. You would have V Thevenin is equal to I Norton times RS. And in both of the cases, RS stays the same. So one thing you'll note when we talk about finding these equivalencies is we will talk about how to find both a Thevenin and a Norton equivalent directly. But finding one is really good enough because the conversion between the back and forth between the two is very easy. So right, if you have a good handle on how to find the Thevenin equivalent directly, then you can always find the Norton with really just one small extra mini step. All right. I want to reorder the way I said some things in the previous lecture, so I'm just looking at this for 1 second. Okay. So what are the characteristics / requirements? And I just put 4 of these. And what I mean by that is the requirements for being able to find a Thevenin or Norton equivalent circuit, and what is also the requirements for that circuit in and of itself. So the first thing I'm going to say is that, right, we can find a Thevenin / Norton equivalent circuit for, sorry, I'll say source. That'll make this easier. So source for any, and this is important, linear circuit composed of sources and impedances. We'll talk a little bit about what a linear circuit is and what linearity is, which should be a review. We'll talk about that a little bit more in a second. But the first level definition we're going to give is that linearity means that it's composed of sources, both dependent and independent, as well as impedances. Now, we're only talking about DC circuits right now, so impedances will mean resistances. But you can do this same process for AC circuits that are composed of resistances, inductors, and capacitors. Another requirement is that in order to find an equivalent, all dependent sources must refer to values within the sub-circuit in question. So what does that mean? If we have a circuit like this with lots of sources and resistors and all kinds of stuff going on, okay, and we're trying to find the equivalent at terminals A and B, this dependent source right here can refer to a voltage X like that, okay? It cannot, assuming that there's more stuff going on over here, it cannot refer to a value out here, okay, because that relationship, there's no way to self-contain that within the equivalent circuit. It's external. So that's what we mean when we say it must refer to. And then lastly, the circuit, the equivalent, okay, the equivalent can only have 2 terminals. And so there can't be any extra grounds, and current sink is just another word for ground, within that equivalent circuit, because that's another way for current to exit that subcircuit. So in other words, right, we need for there to be one path for the equivalent, A to B. Okay? If there's another ground in there, that means that there's a second path. That doesn't mean there can't be a ground in the circuit that you are finding the equivalent for, but the ground has to be one of the 2 terminals, right? So, so that's okay. So the main words here, right? Linear circuit must refer to values within the subcircuit in question, and it can only have 2 terminals. Okay. Next question, which may seem a little bit disjoint from what it is that we're talking about right now, but this is very much connected to what it is that we're doing. So what is linearity and what is superposition? All right. So I am not going to go into writing out the formal definition in words. What I'm going to do is rely on the mathematical definition because that's the easiest to write up here and also tells the best story. Okay? So before I do that, though, what is linearity? What is superposition? You guys have hopefully heard those terms before. Can anybody tell me what they mean? Yeah.
I think superposition is like, it doesn't matter where they're located, but you can add them together in a certain way.
Yes. So why don't we start off with that then? So the principle of superposition tells us that we can essentially, or lets us know that for a linear system, we can treat the inputs as such. So if we have two inputs, which are x1 and x2, and two coefficients, which are alpha 1 and alpha 2, a coefficient times the output associated with x1 plus a second coefficient times the output associated with x2 is the same as applying the function to and this is also the reason why I think it's easier for me to simply write it down mathematically than this describe it. Right? You can see here alpha 1 f of x1 plus alpha 2 f of x2 equals, that's the same as simply applying the function once to alpha 1 x1 plus alpha 2 x2. And so superposition is really a combo of two different other principles. Does anybody remember what those are? One of them is additivity, which we just said. So additivity. And I cannot spell today. There was way too many letters there. A-D-D-I-T-I. Additivity. Okay? So that one refers to our ability to sum f of x1 and f of x2 together. What's the other one that allows us to bring the alpha 1, the coefficient, into it? It has a name that's, it's not like multiplicativity or something like that. Homogeneity is what it's called. Okay, so if both homogeneity and additivity apply, then we can apply superposition, which is both of them together. So this is what it means mathematically. Now, what does it mean for circuits? Okay, so let's say I had, and I'm going to move over to the right a little bit to give myself some space. Let's say I had a circuit that looked like this. So I'm going to call this VS1, call this R1, R2, R3. This is VS2, this is R4, and I'm going to call this V out. Okay. One way that we could solve this circuit is just to go ahead and solve it, right? Just we've learned plenty of methods in order to do that. However, what if I split this circuit up into two pieces, okay? For one, I applied only VS1, and for the other, I applied only VS2. So what would that look like? It would look like this. Sorry, it's going to take me a second to draw it. But I didn't want to make the circuit too simple, or else it wouldn't really get the point across. So this circuit has VS1, but our VS2 is not present. If we analyze that circuit, it'll give us an output which I'm going to go ahead and call Vout1 because it's associated with VS1. Then I split it up into another circuit, or we have a second half where now this only considers your VS2. That's where our source used to be. So what we can do is we can take this, and it'll give us our V out. Okay? So superposition, as far as circuits are concerned, tells us that we can apply independent sources, at least. We can apply independent sources individually, look at their individual effect, and then combine them together, using addition, in order to determine their overall effect. Okay, and we can do this for more than two sources. If there were 3, 4, 100, whatever, you could analyze it each time individually. So what we have here is simply just, right, V out is equal to V out 1 plus V out 2, which is very similar to saying, well, I don't need to write it any other way. That's good enough. Okay, so superposition, linearity, superposition. You can see there's a parallel between our mathematical definition of superposition here and then our circuit-based definition of superposition here. In both cases, what we're able to do is to equate the combined effect of two or more inputs as the sum of their effects individually. Math says it the best. Now, why is this important? We'll come back to this a little bit later. Yes?
How come it would be the difficult to solve for just the original circuit?
So it wouldn't. This is not necessarily, superposition is not necessarily a shortcut, right? It's not something that makes the problem easier. But when we're trying to find this Thevenin and Norton equivalent, we'll see it helps us because we are trying to isolate out two different characteristics, which is R Thevenin, RS I called it, and V Thevenin, and we want to calculate them individually. So the ability to take the sources out of the equation for a second, then calculate R Thevenin, then do the other one separately. Essentially, we'll see when we get to the method, superposition is the basis upon which the method it relies. If the circuit weren't linear and we couldn't apply superposition, then we wouldn't be able to do this the way that we do it. Okay, so let's do what we've done several other times in this class, and let's just go ahead and jump right into an example. And then what I'll do is I'll backtrack a little bit. I'll talk about why superposition and linearity apply or are important to doing it in this way. So I'm going to go ahead and skip right to, okay, an example. So the example is to solve for the Thevenin equivalent for the circuit below. So the circuit looks like this. And if we were going to connect a load, that's where we would connect it. This is going to be our VL, okay, which is our load voltage or our terminal voltage. And these are going to be the points that we've been referring to as A and B. Right? Point A and point B are just these generic names I'm going to give for the terminals of the Thevenin or Norton equivalent circuit. So we want to find the equivalent for all this in here. So what are the steps in this? I'm going to number these a little bit weirdly because some of the steps are like preliminary steps that eventually we're going to drop out and we're going to stop doing. So I'm going to call like the first 3 steps like step 0A, 0B, and then 1 will be the actual real start of the process. So 0A or whatever. Okay. We want to make sure that we properly define the terminals and the area for which the equivalent will be found. And so what I'm going to say for that is properly define the terminals and the load. What that means is draw the orange line, okay, or the orange area. We want to make sure we understand exactly what is inside of the area to be for which the equivalent will be found, and what is inside and what is outside. Okay, if we don't have a proper understanding of that, then we're most definitely not going to get the problem right. Okay. Step 0B. Make sure the circuit meets all the requirements that we outlined above, okay, up here. So what do those consist of? 1, is it linear? For linearity, I mean, there's a formal way that we can check for linearity mathematically, but we essentially will be making sure that it only has independent or dependent sources, constant impedances, which it does. The other thing that we also have to be mindful of is if there are dependent sources, those relationships should also be linear. What that means is that this voltage, if it were dependent, this equals 2 times Vx is fine. 1/2 Vx is fine. 1/2 Ix is fine. Ix squared, that's not okay. E to the Ix is not okay. Okay, because those are nonlinear relationships, nonlinear expressions. That's not something we're really going to see in this chapter, and that's not something you see too much in general. But I thought I would just go ahead and point it out, just for the sake of being thorough. So is the circuit linear? It is. So we're good. There. Number 2, do the dependent sources I'm just going to go ahead and use, say, stay within our subcircuit. And again, what that means is, do they refer to values that are within the orange curve or within the orange area? We don't have any dependent sources, so we don't have to worry about that here. So I'm just going to go ahead and put NA. 3. I'm just going to put, are there 2 terminals / no grounds? Okay, is that the case? And it is. So we're good. So you want to make sure to check for all of those. Okay, now we're going to get to the actual process. So this is what I'm going to call step 1. So step number 1 is going to be to find RS equivalent. How are we going to do that? We are going to, to do so, we short all independent voltage sources and open all independent current sources. So up here, we have an independent voltage source and an independent current source. What happens when we turn the voltage across the independent voltage source down to 0? It becomes a short. What happens when we turn the current source down to 0? It simply just breaks that piece in two. It becomes an open circuit. Hence, that's why it's defined as such. So, let's go ahead and redraw the circuit, which is really easy to do. If you look at what's shown here, if the voltage source becomes a short and the current source becomes an open circuit, then all you're left with is the 2K and the 1K resistor. So you're left over with something that looks like this. 2K. Okay, and those are where our sources were. Now, we find our equivalent resistance is just equal to whatever the equivalent resistance is between terminals A and B. So what's the equivalent resistance between terminals A and B? 3 kilo ohms. So we've solved half the problem. So next, we want to find Thevenin. In order to do that, we're going to analyze the circuit in a no-load or an open terminal condition. And so what does that mean? Simply just means there's nothing there, which means that that's the case. All right? So we'll have to redraw the entire circuit. But our sources will stay there. And so in this case, what we have is IL equals 0, and I'm going to call this the load voltage when there's no load. That's what NL stands for. So this is a pretty easy circuit to solve. We know if we apply KCL at this node right here, we know that the current flowing in this direction has to be 2 milliamps, right? Because none of the current is flowing to the right. It's all flowing to the left. And then we can figure out what this voltage is here, which I'll call V1. That voltage is equal to 2 milliamps times 3 kiloohms, right? So that's 6 volts. And then lastly, we know that VL will be equal to V1 plus 3 volts. That's just applying KVL. And so we're left with a value of 9 volts. So that is the other half of the answer. I'll give everyone a second to look at that. So we eliminate the sources. We solve for the equivalent resistance across the terminals A and B. That's our source resistance. We remove the load and open it up so that it's an open circuit condition, open terminal condition. And then we go ahead and solve for VAB again. And that value, which we call VAB no load or VL no load, that is the Thevenin voltage. Next, we can just show the solution. We have both the values, so it's just a matter of putting it in the right circuit form. So if we were to show it as a Thevenin source, this would be 9 volts, and this would be 3 kiloohms. If we were to show it as an equivalent, a Norton equivalent, then this is still going to be 3 kiloohms. What is I Norton going to be? Remember, we talked about how to do the conversion. We said it's just dependent on Ohm's Law. So what is it? It's going to be 9 volts divided by 3 kiloohms, which means it'll be 3 milliamps. So those two are both valid solutions, and they both are equivalent to the circuit that's shown up here. So now let's talk for a second about why we talked about superposition and linearity and all that good stuff and how that applies to the way that we do this. So what's going on here? The basis for this method, you can see, is splitting up the circuit into essentially two different versions. This right here only works because of superposition and because of linearity, and that's again the reason why it's a condition for finding the Thevenin or Norton equivalent that the circuit is linear. If superposition didn't apply, we wouldn't be able to find the equivalent resistance by simply pulling the sources out. Okay, that's a capability we get because of superposition. And then, in the similar vein here, we wouldn't be able to simply put them back in and solve for the no load condition. So our ability, without going into too much detail and without getting too long and convoluted on this, right? It's superposition which allows us to do step 1 and step 2 separately. Okay. So, any questions on this, maybe on what this means, why this is useful? We talked a second ago about, well, why is this useful, right? It doesn't make, we said superposition, doesn't necessarily make it any easier to solve the problem. But our Thevenin and Norton equivalents definitely make it easier to solve the problem, right? If you were trying to look at 500 different types of load or different load values and their effect on the circuit, it would be much easier to analyze this every time as compared to analyzing this every time. Okay? And then as the circuit gets more and more complex, as long as it stays linear, the equivalent circuit doesn't get any more complex. It stays the same. All right, let's take a look at a second example. We're just going to go ahead and get started on it, and let's see how far we can get, then we'll pick up with it next time. All right, so we haven't talked about dependent sources yet. Our method, specifically step 1, doesn't work for a circuit that has dependent sources in it. Give me 1 second to pull up the other version of the notes. Okay, so the main problem here is that we can't simply zero those out because we would be eliminating the relationship that they represent. So again, we're gonna tackle this by trying an example. So solve for so we have a circuit with dependent sources. What does it look like? Give me 1 second to draw it. Okay, so this is 2 kilo ohms, this is 1 kilo ohm, 2 kilo ohms, this is also 1 kilo ohm. We're going to call this value Vx right here. And this is 2 times Vx. This is 5 volts. All right. So, and then this is A and B over here. This is A. This is B. This is our voltage VL. And so we're trying to find the equivalent for everything in there. All right. So now we ask ourselves, so we can still, fortunately, we can still find VTH using the open circuit terminal case. So that's good. So this step 2 right here, that's not affected by whether there's by the presence of any dependent sources. We can still solve for what VL is when there's no load attached. Good. And I'm gonna rename this because I want it to match the other one. So I'm gonna call this instead of no load, I'm going to refer to it as open circuit. But now the problem is we cannot find RTH in this or RS in the same way. Okay. So what are we going to do instead? I don't know why I wrote this like this. This is step 2. This is step 1. Next time I want to change their places just so it matches with the previous. Okay, so what are we going to do instead? What we're going to do we're going to short the terminals. of A and B. We're going to short A and B together, and then we're going to solve for what the equivalent resistance is in that case. I'm going to hold off from going into too much detail there because I think, again, when we go and do the example, it'll be the best demonstration of how that works. Okay, so going back to the problem, because we kind of got off track for a second. So going back to the problem, so step 0A and B, let's make sure we do both of those. We want to properly define the terminals and make sure it meets the requirements. So properly define the problem and make sure it, I'll say, is suitable for an equivalent. So I'm going to do that quickly. Take a look at the circuit. We do know what we're solving for because we already outlined it in the orange. We've clearly defined what our terminals A and B are. We know what VL is. So again, we're trying to find the Thevenin or Norton, well, either, equivalent resistance for the circuit that's shown inside of the orange. Is the circuit linear? It is. It's composed of only sources and constant impedances. This dependent source is a linear expression, 2 times Vx, so we're good there. Does the dependent source refer to values that are within the subcircuit in question? It does, because Vx is included within the subcircuit. And then lastly, are there any additional grounds or any current sinks in there that we could potentially count as like a third terminal? No. So we have 2 distinct, well-defined terminals there. So that covers all of our bases. I know I'm going through that part quickly, but you don't want to forget about it because, one really great way to trip up people, not that I don't like to do that too much, but to trip up people on a quiz or an exam would be to give one where it didn't meet one of those requirements, and the answer was simply, we cannot find a Thevenin equivalent for the circuit. All right, so I'm just going to put a yes here, / OK. Everything is suitable for what it is that we want to do. All right, so step 1. I'm going to keep it in the same order as before. We want to find RS. To do so, we're going to short the terminals together. So what is that going to look like? Let me see if it'll let me. Okay, so what are we going to do to short the terminals together? We are going to, no. All right. So we're going to short these two terminals together, which is going to essentially, right? Anytime we short, we have a short path in parallel with a resistor. That resistor will no longer have any current flowing through it, so we can just eliminate it from the circuit altogether. And so what we're left with is a circuit that looks like this.